This is quiz 8 and is on the basics of chemical equations and reactions. Right there. Is that readable? Okay. Now, the issue with chemical reactions is that it is honestly a shorthand method of representing a chemical process. And in the notes I've given you, there are several methods or types of writing chemical reactions. Molecular equations, I'm going to make that list because we're going to emphasize this in a few minutes. Types of equations. You have molecular, you have ionic, net ionic, now these are the three I've emphasized in the single replacement reactions, which I'll show you more about in a minute. But there's also one referred to as a structural equation, in which the structure of the molecule is shown it shows how the structure is laid out. You'll see all of that in organic chemistry types things. From time to time I will use that to emphasize a point. But for the most part on chemical equations, the top three will be part of your course from here on, almost every time you show up. Okay, just wanted to kind of illustrate that. Okay, all chemical reactions must conform to the law of conservation of matter. Also, conservation of charge. And I haven't really emphasized that over the balancing of the equations. So, reactions must conform to 1. Conservation of mass, that's balancing the equations, I think you see that, and 2. Conservation of charge. Which means in an oxidation reduction process, the number of electrons transferred from one element to another element has to be equal. If one element loses 2, another element has to gain those 2. They're not just lost into oblivion. I think you appreciate that. So in question 1, how do we know if an equation conforms to the law of conservation of matter? Well, that is the law of mass balance, which refers to the sum of the masses of reactants equals sum of the masses of the products. It does not refer to numbers of particles, number of molecules on the left and right. It does apply to the number of elements. You can check your balance by looking at numbers of elements. If the charge structure is not given, it's a little tough to follow the charge issue. But the law of mass balance is the foundation that you should always check for working any chemistry problem, that the reaction is appropriately balanced. So in the list of answers, it was mass reactants equal mass of products. Now with that, I gave you a combustion reaction for methane, and then C2H4, that's ethylene. Okay, C2H4 is a gas plus O2 gas. Make a note of this in your brain, please, on notes. If you see a hydrocarbon, that means a hydrogen carbon or any organic compound, and then on the reactant side it is attached to oxygen, it refers to a combustion reaction. The one you are responsible for on the short term right now is a hydrocarbon combustion. There are nitrogen compounds that undergo combustion and do something. There are halogen compounds that undergo combustion and do something, and so forth. But in the hydrocarbon combustion, you only get two things, always, regardless of what's over here in the organic compound. It's CO2 gas and water. Now, it doesn't matter whether you put that right now, liquid or gas, water vapor sometimes present. But when we talk about combustion reactions of hydrocarbons, there's only one set of products. Please make a note of that, regardless of what we have here. Now, balancing equations. Now, I haven't balanced a ton of equations, which maybe I should have, but the issue is most people have a lot of practice in balanced equations. Now, some of the techniques that you may not know about in balancing an equation, if you see an element by itself, maybe whether it's basic standard state or whatever, save that item to last, because you can use a fraction in there. It's legal. 5/2 to balance the equation. That's not in this one. So C2 needs two carbons over here. And also check mark, once you put a compound down with subscripts, you can't change the subscripts to help balance an equation because of the the molecular identity. If you change the subscript, you change the molecular identity. It's something else. H2O, okay, becomes H2 to balance a reaction. That's not legal in that this is hydrogen peroxide, different chemical and physical properties than water. So once the subscripts are set into the formulas of the compounds, you can't change those. So the only way we can change numbers now is with coefficients like this, and all of this I'm sure everybody already comfortable with, and practice never hurts, and review never hurts. Okay, next one would be hydrogens. Well, I got 4 here, and I got 2 there, so I can put a 2 right there. Then I count my oxygen. 2 to 2 is 4, 5, 6. So it's real easy now to put that one in that context. C choice in here. Trying to think of one. This one, right here. Jot this down on a piece of paper, so because I do put this kind on the big exam. Okay, so if you get, I'll give you a fraction thing and why you use it. Many of you already know. I'll leave the oxygen to last in the balance, so I will work with the carbons. I got 3 carbons, so I'm going to need 3 over here. Then hydrogen, I got 6. I only have 2 here, so I'm going to put a 3 right there. So now I count out my 2 times 3 is 6, 7, 8, 9. 9 oxygens. Well, how do I balance the oxygens if I've got 9 over here and 2 over here? It's legal to put a 9 halves in there. Okay, now the point here in using this 9 halves, this refers to something like 9 over 2 times 2 over 1, which is equal to 9. So we're not giving up the basic standard state, but we're adjusting it stoichiometrically or mathematically so that it matches the numbers left and right. And there's nothing wrong with using a fraction and balancing an equation. If you wanted to change that, multiply through by a 2. And it's the same equation in terms of the structure. The thing that changes if you change coefficients is the kinetics of it, and that's the second semester topic. And so I'll leave that in that. Leave that as is. It is a kinetic thing if you change the coefficients. And then multiply by 2, you get 9O2 as a gas going to 3, 6. That'll under multiply. 6CO2 gas plus 2, 3 is 6H2O, and we can list that as a liquid. These essentially for your purposes are the same. Here are the decomp reactions we studied. And the first letter in each of these constructs an acronym, Coach E. And I think I sent everybody an email last night trying to give you some extra work to do and clarifying some things. So you must memorize this set and the outcomes, because you will have more problems that ask you what is the outcome of a chlorate. Now the problem is a chlorate, metallic chlorate, and it's going to give you a salt, an oxide. Now salt, please mark this down, is also an ionic compound. Salt, and the word salt equals ionic compound. And it consists of a metal and a non-metal. The only one that doesn't is ammonium, whatever. Okay, so that's the only cation we're going to use right now. So this would, based on the chlorate, you got bromates nowadays also, based on the chlorate, this would be a chloride salt. The metal chloride, metal say potassium chlorate, this would become potassium chloride and O2 in basic standard state. So that's, you need to study that and review the video if you need to on the examples that are used, and that'll help you along on this. So it simply says metal carbonates in this case yield what? Okay, metal carbonate will give you a metallic oxide and a non-metallic oxide. All right, if we took, say, calcium carbonate and heated it strongly, we need to get out of this a metal oxide out of this and a non-metal oxide. Now understand this, and this may help a lot in comprehending the issues going on here. Whatever you put over here as a product has to come out of what compound you have over here. You can't put stuff over here on the product side that ain't on the left side. And that's just kind of one of those logics. So whatever you put over here has to have a calcium, a carbon, and some oxygen, 3 oxygens. Now if we have a metal oxide, here's your metal. So why don't we do this? Calcium oxide. Lousy O, but okay. That's the start of writing any product compound that you are asked for in questions like this. Now, it may or may not be the correct combination in terms of numbers of elements, but when it says a metallic oxide, you put metal and oxygen together, and that's a start. How do you know if the compound has the right number of elements? You better know that? What, Josh? How many, what do you add up?
The charges.
The charges, that's right. You add the charges, and if it comes out to be, what?
0.
0, then you've got the right numbers of elements. Everybody good on that? Sum of charges. So after putting the elements together, and I'll emphasize this a lot today when we get into the metathesis work, when you put the elements together, The next thing is identify the oxidation states. That's why I dug out that rules of oxidation states. In case you run into one, you look at the rules of oxidation states. Now, I taught you some off of the periodic table, and that's useful. The rules of oxidation state, I think, will carry it another level. Okay, and a non-metallic oxide. Well, carbon is the only other element in here, and it's non-metal, so we'll put a carbon down here, and oxide. Now, is that correct number of elements? Not exactly. Two ways to deal with this. Oxygen always is a -2, then you could look at carbon as a +4, and then switch 2 down to 4. Well, you need to reduce that to CO2. There's no C2O4 floating around in the world. A second way to deal with this is you've already used one oxygen. This to me is easier. You make your calcium oxide. You've used one calcium, one oxide. What's left? One carbon and 2 oxygens. Why don't we just go CO2 out here and make that a gas? And this turns out to be a solid. Just drop the oxygen back by 1. This same thing works with sulfates. Sulfite. Let's do the sulfite like that. It goes to a metallic oxide and a non-metallic oxide. Right there. Metallic would be magnesium and oxide. MgO. That's a solid. +2, -2. So we do not need any subscripts now. What's left? A sulfur and a couple of oxygens. Well, all right. So we go sulfur and 2 oxygens, and that's your answer. So if you know the list right here, and you say carbonates, well, I'm metal oxide, non-metal, you can build the product side over here right out of the compound to give you. Metal oxides, okay, goes to a metal. Well, put the metal and molecular oxygen, always. Oxo acids, that's your polyanion acids. Non-metallic oxide, okay, SO2 or whatever, and water. You know what water is. Chlorates, salt, which is of the chlorate, metallic chloride, and so forth. Hydroxides, metallic oxide, you write it's like sodium hydroxide, you write NaO, and then throw in water. Electrolytic products may be a little different to you, but when I say basic element standard state, you'll always have an ionic compound over here. Which is a metal bonded to a non-metal. When you put that into water, it breaks up between the metal and the non-metal. And you have a metal ion and a non-metal ion. Then all you do is look up in the back of the book and thermodynamic tables. Well, if I have sodium, for example, right here, what's the standard state? So I look up, I find the 0 under delta HF, and it turns out to be sodium. And then I say I got chlorine, a chloride, say Cl minus, goes to Cl2 over here, or chloride over here, chlorine. What's the basic standard state? Well, it's one of those diatomics. And so you have to have a little extra support here when you're answering this last one. That is the thermodynamic table. And problems on the exam, I will either provide that table as a reference sheet or include it in what you need in the question. Okay? So I'm not going to leave you hanging with something like that. Any questions about that? Looks like that was C choice in mix here. Now I'm going to give you a short lecture on electrolysis. Electrolysis uses what we call a electrolytic cell, a battery jar, maybe some of your, and in this you have a salt solution or salt melt. You can use either one of them, okay? In this structure, you have electrodes that are placed down into this solution. And then this is connected to a transformer or battery. Short side of the symbology is negative, the long side is positive in the symbology that you have. When a salt solution exists, regardless of the compound, sodium chloride, you have sodium ions and chloride ions. If you have calcium bromide, you have calcium ions and bromide ions. And those are plus ions floating around independent of the negative ions, and negative ions floating around independent of the positive ions. When you close the circuit up here, one side or one electrode is negative. For example, this one is negatively charged all the way around. This plus ion will migrate to that electrode. Plus means you are deficient in electrons. And so it'll start sucking electrons off of the electrode. When a substance gains electrons, how do we define that in terms of oxidation reduction? Anybody? Substance gains electrons. Is it oxidation or is it reduction? It's reduction. Gaining electron, you're gaining negative charges. So when this occurs right here, it's a reduction process. The other electrode is a positive side of the battery. And of course will attract the negative ions. Only thing that moves or transfers in this system are electrons. So we are losing electrons into this electrode. So if this is losing electrons, how do we identify that? Oxidation or reduction? That's right, oxidation. There's no other. There's either oxidation or reduction. So this process is oxidation. Now, one thing I didn't emphasize, and this is important for this material, what you're looking at here as the elements or substances migrate to those electrodes is a process. However, there is terminology to identify the item undergoing oxidation reduction. Though this item right here, the cation, which undergoes the reduction process, is called an oxidizing agent. The individual elements in the reaction, individual elements, and they're always on the reactant side, are called oxidizing agents. This is the individual element reduction process of the entire reaction. The oxidation process, you use the opposite terminology for the agent. So oxidation would become a reducing agent. That is, the positive ion causes something to undergo oxidation. The negative ion causes something to undergo oxidation. That's why they are given individual terms like that. But in the study of electron transfers and chemical reactions like this, and oxidation reduction reactions, The terminology is critically important that you understand and are able to separate that terminology. Somebody comes up and says, well, this is undergoing oxidation. Your brain says, okay, that must be the one that is a reducing agent. If you're undergoing oxidation, that's got to be a reducing agent, and so that's the one that's giving up electrons. So you have to mentally get comfortable with dealing with things like that as you learn oxidation reduction, and we're going to emphasize that in a few minutes. But the process of passing a current through a solution or a melt of an ionic compound results in oxidation reduction, and the outcome is basic elements in their standard state. If you're working with, say, a sodium bromide, when the process is complete, you have sodium in its basic standard state, and bromide converts to bromine in its basic standard state. Well, if that's a decomposition, that's one terminology you need to understand. The second thing is, well, what's the process that's going on? Okay, the sodium became sodium because it gained an electron reduction. Bromide becomes bromine because it gave off electrons and underwent oxidation. And we'll say more about this in a few minutes. This ABCD. Okay, and the question, of course, was which one produces oxygen on heating? That particular question and the answer is not the most important issue here. I put down in all four cases there is a decomposition outcome, and you have to get that in your mind relative to the Coach E acronym. And you can certainly expect several questions to depend on you getting that and being able to deductively put the products together. Well, this is a sulfate, and when sulfates break down, it's kind of like the carbonates. So if you have you can carbonates, and you can put in this also sulfates, sulfites, nitrates, nitrites. All of those will follow the same outcomes, and you'll see those today when we do the driving force in gas decomposition reactions, because they follow the periodic table. Run these out and as practice, and take that email I gave you last night and see if you can work through those. Now, the essence of this is, first and foremost, write the compound elements together. Do not take subscripts. You will take subscripts to the product side if the polyion stays together. But see, this gives a metallic oxide. So the outcome of this will be sodium and oxide. So I'm just going to put sodium and oxygen together just like that. It may be right numbers, it may not be right numbers of elements. But the rules say it's going to make a metallic oxide. Okay, well, the only metal in that formula is sodium from the left side of the chart. And it produces a non-metallic oxide. Well, I have the only non-metal here is the sulfur, so I'm going to put that together. That's step one in predicting the outcomes. Step two is assign oxidation states, and I told you to use -2 for oxidation states until I tell you otherwise. Okay, sodium +1. So I need 2 of these so that the sum of these will Give you 0. So I need 2 sodiums, or I can bring it down like that. The easiest way to deal with this, now in doing this actually sulfur's a +4 in this. It's a cation. It's not an ionic compound which conforms to the periodic chart, and that it is in the 6th group and loses 2 and takes on 2 electrons, comes -2. You don't have a -2 oxygen and a -2 sulfur in the same compound. One of them's got to be a cation, one of them has to be an anion. Well, I've already identified this one. Well, this is not a +2. It's a +4 in reality. And if you switch these, you'd reduce the subscripts in this case. The easiest way in all of these, in everything that we do here, the non-metallic oxides will drop down by 1 oxygen. And that's the corrector. Same way with the carbonate. It's a metal oxide, so I'll have a calcium oxide, and then I'll have a non-metallic oxide, and the oxygen drops down by 1. You use 1 oxygen, you can do that. That's correct. Those are solids. This is the one that you were supposed to choose. C choice. This is a chlorate. The chlorates break down into metal salts, that's what I'm trying to say, a salt of the halide that's in the system. It could, in this case, chloride. Chlorate goes to chloride and then gives off O2. So the chloride salt in here is simply KCl, right here. And molecular oxygen is the outcome. Always use O2. We're not going to make ozone out of this. 3. Okay, and I put a 2 here and a 2 there, and that balances the equation. But when it says salt, that's also ionic compound. Now that salt is the metal and the anion primary in that structure, because you're going to use all the oxygen. So the only salt in there is the metal nonmetal. It's you're working with right there. This goes to a metal oxide and water. Okay, like this, like that. So you have to practice forming those products from the Coach E acronym and the terminology that I've given you. Go back, if you haven't seen the email, I'll give you a list down there that follows the acronym, and hopefully you can get a handle on this